Well, now you've got more possible ways of arranging that system. Okay, you've increased the entropy. Okay. What I'd like to do is apply the second law of thermodynamics to a very simple example. This example is chosen so that we can get away from a lot of the complex mathematics. Okay, and if you're saying, well, what does the Sun-Earth system have to do with evolution? It actually has quite a lot to do with it, and we'll see that the results here of this example we can then apply to the idea of morphogenesis, the idea of let's say an organism growing up from a simpler, like an embryo or something. So this example here, let's take a look at what would happen, okay, if a very small amount of energy, let's say 100 joules of energy, travels the 93 million miles, okay, through empty space from the sun to reach Earth. And let's assume that it gets completely absorbed by the Earth. Okay, to be able to apply the second law, well, we need to know what's the surface temperature of the sun. It's about 5,700 Kelvin, and that of the Earth, we'll say, is about 290 Kelvin. Let's calculate the entropy change in the universe for this process. So we're going to take a look at the second law. Okay. First, it's important to realize that to calculate the entropy change of the universe, you've got to take into account the entropy change of the Earth as well as the sun. Okay, that these are two objects that are really both part of our system. Okay, well, here's our mathematical definition and of entropy change for a process. This is sort of nice because the Earth and the sun are so massive that adding a small amount of energy, like 100 joules to it, isn't going to change the temperature significantly. So the nice thing about that means we can take the temperature out of the integral, okay, and when we integrate the differential, we've expressed it in a much simpler form, okay, that the entropy change of the universe is really a measure of the heat that gets added to the Earth, okay, divided by the Earth's temperature, plus the heat that gets removed from the sun divided by its temperature. When we plug in the numbers here and take a look, okay, 100 joules of heat enters the Earth, 290 Kelvin, the temperature of the Earth. The sun loses energy, so we put in a negative 100 joules divided by its temperature. Okay, when we get out our calculator, plug the numbers in, we see that the entropy change of the Earth is positive, but the entropy change of the sun is negative. But take a look, the overall entropy change of the universe is positive. That's what the second law of thermodynamics tells us, that the entropy of the universe increases. Now here's the thing, if you just chose to look at the sun, you might very well believe that the second law of thermodynamics was being violated because its entropy is going down. Okay. But if you want to apply this law, you've got to look at both the sun and the Earth, okay, to get the complete picture. Okay, so what happened here? The entropy of the sun decreases as heat leaves it. Okay, the entropy of the Earth increases as heat enters it. Okay, but the entropy of the universe increases. Okay, why? Well, the increase in entropy of the Earth far exceeds the decrease in entropy of the sun. Okay, well, from a statistical mechanics point of view, how would we explain this? We'd say that there's many more microstates available to the cooler sun, warmer Earth scenario than for the warmer sun, cooler Earth, and that this process of heat flow then is statistically favored. Okay, a simple matter of probability. Okay, it involves an arrangement of energy that is statistically more probable. Okay, according to the second law of thermodynamics, systems cannot move spontaneously to states of lower entropy. Okay, now, words of Henry Morris, every system left to its own devices always tends to move from order to disorder. Okay, so this simply is not true. Okay, as we saw, when you apply the second law to a process, you must consider the entropy change of the environment as well as the entropy change of the system. Okay, if we chose just to look at the entropy change of the sun, we might think the second law was being violated. Okay, the second law definitely allows for localized entropy decreases, okay, so long as there's greater entropy increases elsewhere, okay, that the entropy of the universe will still increase. Okay, so let's take a closer look at Okay, this example of morphogenesis, we're looking at the development of a mature human being from a simpler embryo. And we're asking the question, does biological growth from a simple organism to a highly complex one, does it violate the second law? Okay, so if we consider our system to be a human being at various stages, okay, or any other organism for that matter, said earlier that organisms are open systems. They exchange matter and energy with the environment, okay, and that in order to grow, okay, you've got to take in both matter and energy, okay, basically in the food we eat. If we look specifically at the processes of digestion and excretion, okay, what's going on? Well, okay, you're taking in very highly ordered, low entropy, okay, food molecules, okay, complex proteins and starches. You're digesting them and you're excreting them as waste products, okay, in the form of, okay, very simple, okay, less ordered molecules of much higher entropy. Okay, metabolism, same idea. When you metabolize, okay, food, you're converting low entropy chemical potential energy, okay, from the food you eat, okay, into high entropy thermal energy. Okay, so clearly organisms they're not isolated systems, okay, that matter and energy is being exchanged with the environment. Okay, so if we want to apply the second law and we say that our system is the human being or whatever organism you're looking at, you can see that, yeah, the entropy of the system may go down, okay, as the organism grows and matures, but the entropy of the environment increases even more. Okay, so that when we look at the total picture, the entropy of the universe is increasing. Okay, if you want to sort of look at this qualitatively, you can say that in our development, the amount of internal order that we may represent, the entropic order, is going to be far exceeded by the amount of entropic disorder that we create in the process of development, in the process of growing. So there really is no contradiction, okay, that even when you take a simple, an egg and a sperm and you look at the quite complicated organism that results, okay, the entropy of the universe is still increasing. Okay, if we want to sort of extend this idea of morphogenesis to evolution, okay, well, if we agree that if morphogenesis is in agreement with the second law, and I don't know if the biology folks would agree with this. I mean, I'm not a biologist, but Richard, tell me what you think. If you say that evolution is really nothing more than the observed change in a gene pool of a population over time.
That's good.
Okay. Then evolution should be in agreement with the second law as well. Okay. If it's really just a matter of, okay, if species developing and growing, if there's no violation, then, why would there be any violation if the species change slowly? Okay, this I think I'm going to skip. This is sort of an interesting idea that, that I've come across in some of the creation science literature. Okay, the improbability of abiogenesis or complex design, but we're going to skip this and go to. I'm sure there's a faster way to do this here. Okay, let's take a look at this. Another common misconception that you come across in the literature is that a mechanism in the form of a code or program is required for order to arise spontaneously from disorder. Okay, I'm not going to read this. I'll leave this up for a little bit, but this is a quote from Henry Morris. Okay, so the idea here being that if you're going to get order spontaneously arise from disorder, there's got to be some sort of mechanism or code that directs that. Okay. I'm going to show you in a second lots of examples that require no code or mechanism, okay, but examples where order spontaneously comes from disorder. And here, any uphill process where the entropy decreases and order increases, we can think of that as an uphill process, it can occur spontaneously, okay, by being coupled to a more dominant downhill process where the entropy increases. Okay, the only mechanism that's required is a source of high-quality, useful energy that can flow. Okay, and this is an analogy, but I think it's a good one. And Henry Morris was by trade an engineer, so I think he would have been familiar with the self-operating ram pump. But the idea here is that you can take water from a reservoir, and you can get that water, if it can flow, you can get it to pump part of itself up to a higher elevation. Okay, now it may appear that that would violate the laws of thermodynamics, but okay, it does that, okay, only when you have this continuous flow of water downhill. Okay, so if you chose just to look at the uphill flow of water, you might think there's a violation, but this happens, and I don't know if you can see in the picture that water from the high elevation reservoir is allowed to flow through a system of conduits and valves to a lower reservoir, and in the process pump part of itself up to a higher elevation. Okay, in the same way that when heat flows from a high temperature reservoir to a low temperature, it can convert some of itself into useful work and energy, but not all of it. Okay, but without going into a lot of detail here, we'll take a look at some examples of non-living systems that spontaneously produce order. Okay, one, snowflakes here. Okay, that if you look at what happens, you've got a lot of randomly moving water molecules which spontaneously give up thermal energy into the atmosphere, and in so doing create very, very orderly arrangements. Okay, which are not alike. I mean, these snowflakes have this six-sided crystalline symmetry, formed spontaneously. Okay, there's no genetic code that exists to direct the growth of snowflakes. Okay, it happens spontaneously. The entropy of the snowflakes may decrease. Okay, their entropic order may be greater than the water from which they came, but once again, the environment, the entropy of the environment increases. Okay, as energy leaves the water to the environment. Okay, other examples, I won't really talk about sand dunes. Think about sand dunes forming. Tornadoes, okay, we've got order from disorder, stalactites, graded riverbeds, okay, thunderheads, okay, and the lava lamp that you see up here. Okay, this is sort of a nice analogy. If you've seen a lava lamp when it's turned off, you just sort of have this gelatinous blob of material, okay, but once you have this nice source of high-quality energy that can flow, and then a high-quality energy comes in the form of the electric current, okay, you create these nice orderly convection patterns as you get that, the blob to, move up and fall. Well, you can sort of see that there's some order to this, but you remove the downhill flow of energy, okay, which is this high-quality electrical energy which gets converted into low-quality thermal energy, and all of a sudden that order disappears. Okay, so it's only by being coupled to a more dominant downhill process that you get the order. Okay, so in all of these examples that I've given, they're spontaneous. Okay, they illustrate order production in the uphill process. They're coupled to a more dominant downhill process. Okay, they correspond to an increase in entropy of the universe in agreement with the second law. And they're driven by conversion of useful forms of energy into less useful forms. They do not require any sort of intelligent program to achieve the order. Okay, if you look at evolution of life in the biosphere, take a look at the downhill flow of energy that is provided by the sun. Okay, that the thermonuclear fusion of the sun provides this very high-quality energy in the form of the photons that we get here on Earth. And organisms on the Earth and the ecosystems can tap into this energy flow and create order, localized order. Okay, that the spontaneous order that we see evolving around us, okay, can happen only because there is this downhill flow of energy, okay, from the sun in the form of food. Okay, and second law is not being violated, that the localized entropy decreases, okay, happen. There's still an overall increase in the entropy of the universe here. Okay. Last misconception we'll deal with, this is very similar to the other one, the idea that self-organizing systems are neither natural nor spontaneous in nature. Okay, here's one statement which is pretty succinct here, that a watch must have required a watchmaker, a car could not have formed itself from parts. The idea being that there's got to be some sort of external agent, some sort of intelligent designer in order for order to spontaneously appear. Okay, this may seem surprising, but what a lot of the science of non-equilibrium thermodynamics is showing us is that spontaneous ordering, that is the expected result. Okay, and there's a lot of experiments. I'll show you one which, suggests that. Okay, here I'm just saying that these self-organizing systems can be understood in terms of this fairly new theory of non-equilibrium thermodynamics. Okay, a guy by the name of Prigogine won a Nobel Prize for this in chemistry in the late 1980s. Okay, so the idea we're going to address is, why is it that our world is in the order production business? Okay, why is it that we see this spontaneous order being created? Okay, what's the cause of it? Okay, well, first we got to sort of revisit Boltzmann's his interpretation of the second law of entropy. I mean, Boltzmann argues that the second law is simply a result of probability. Okay, when you're talking about systems that are at equilibrium or very near equilibrium, systems of colliding particles, this may be true. Okay, but the problem is that the more we learn about the surface of our Earth today, I should say Boltzmann's system, it applies to systems near equilibrium. Okay, we're finding more and more that our world is not at all a system near equilibrium. Okay, like Boltzmann's ideal gas in a box. That our Earth it consists of all sorts of gradients, temperature gradients, pressure gradients, composition gradients, which make it very different from a system in equilibrium. Okay, this theory of non-equilibrium thermodynamics, in a nutshell, that when you subject a system to naturally occurring temperature, pressure, and composition gradients, sometimes called potentials, that this spontaneous ordering, that it happens. Okay, the systems can transform into highly non-uniform, highly organized configurations. Okay, and when the gradients become larger, this happens more and more. Okay, this last idea is pretty profound, that nature will create systems, sometimes very complex systems, simply as a means of eliminating gradients, of doing it as efficiently as possible. It turns out that if you create organization, that organized systems are much better at reducing gradients, differences, than less organized systems. Okay, so this sort of gives a basis or a reason why we might find order. Very simple experiment here that was done, showing this, the Bernard experiment. Really simple idea. Bernard just took this viscous liquid and stuck it on a burner. Well, the burner was, pretty uniform heat source, and the top surface of the liquid was just exposed to the air above it, so it was at a lower temperature. So we got a uniform heat source below, cooler, uniform mixture of air above. And the temperature difference, this temperature gradient from below and above, could be controlled for the sake of the experiment. And what Bernard found, and what everybody finds when they repeat this experiment, is pretty amazing. Well, when the temperature gradient is low, when there's not a big temperature difference from below and above, you get what Boltzmann expects to happen. That when the temperature gradient is below some critical threshold, the Okay, the flow of thermal energy from the bottom of the liquid to the top is in the form, it's a very disorderly flow. It's in the form of, well, in physics we call it thermal conduction. It's just a random disorderly collisions between molecules and they exchange energy. Okay, and the entropy of the system increases. Okay, and when you look at it, you can see a picture to the right. The macroscopic state, it appears very uniform, okay, very homogeneous. Okay, you don't see a whole lot of order there. But, okay, when that temperature gradient gets big enough, okay, all of a sudden we see the spontaneous order produced. So when delta T is above some critical threshold, okay, this order spontaneously emerges as you get hundreds of billions of molecules to collectively now move from the low temperature to the high temperature in very organized cells, these called Bernard cells or convection cells. And they do this because they can very efficiently eliminate that gradient. Okay, so in this case you see that, yeah, the entropy of the environment may increase, but the entropy of the system goes down, okay, as these very, very organized cells form. So you can see the picture up at the top, okay, looks very different from the macroscopic state we looked at when the temperature gradient is small. And there's sort of a schematic of what one of these convection cells looks like. Okay, in this case, the macroscopic state appears very non-uniform and highly organized. Okay, so if we look at this, the rate of heat flow in the disordered regime, well, we could express it with an equation here. This is what a graph of rate of heat flow versus temperature gradient looks like. Okay, and you see that there's a certain slope to the line here. Okay, but when we get into that ordered regime, okay, all of a sudden the slope of that line gets a lot bigger. Okay, that tells us that, okay, well, this discontinuous increase in the rate of heat flow following that disordered order transition, okay, that the rate of heat flow suddenly increases dramatically, okay, once you have order. Okay, now if you think about, rate of heat flow, okay, what is the significance of that? Well, the rate of heat flow, remember, heat flow goes like entropy. Okay, so the rate of heat flow is proportional to the rate at which entropy is produced. Okay, and saying in this picture, note the dramatic increase in entropy and the rate of entropy production that happens with that switch from the disordered regime to the ordered regime. Okay, it seems like, okay, the system is able to, will produce entropy at a much faster rate, okay, when order is created. So, okay, the weird thing, according to Boltzmann's hypothesis, the second law, self-organization appears infinitely improbable. It wouldn't happen when you're talking about systems that are near equilibrium. Okay, but here, we find that order emerges in these Bernard cells with 100% probability. Okay, so when you get these gradients and the gradient gets big enough, okay, order is spontaneously produced. Okay, we find that the order production is entirely opportunistic. It will occur whenever it gets the chance. Okay, why is that? Okay, this may be the most important statement here. It turns out that ordered flow is much more efficient at minimizing the potentials, at getting rid of gradients than disordered flow. So this provides a reason why we see order spontaneously emerge in our world. Self-organizing systems, they don't occur near equilibrium, okay, only within the organizing confines of a gradient. Okay, this, again, the law of maximum entropy production here. Okay, why is our world in the order production business? Okay, statement of it says this, that a system will select the path or assembly of paths out of all available paths that maximizes the entropy at the fastest rate possible given the set of constraints that are imposed upon it. Okay, we see with the Bernard experiment, okay, that, and this is amazing, if you actually change the shape of the container, okay, that viscous liquid it is in, if you, now it didn't reproduce very well, but you can see that the nature of the cells, the nature of the order produced gets very, very different. Okay, that somehow when you alter the constraint, okay, you change the pattern of order created. Why is that so? Well, because the system is automatically going to seek, okay, a way to minimize the potential as quickly as it can. Okay, so the cell system evolves, which reduces the heat gradient most efficiently. Okay, think about this. This is sort of an obvious law if you think about what happens in your own house in the Modesto wintertime. Okay, there's, hopefully if your heater's working inside, there's a temperature gradient between inside and outside. Okay, well, what happens? I mean, heat typically flows from, thermal energy flows from inside to outside. Okay, and most of this heat transfer takes place by conduction, and the heat will go, through your windows, through any cracks in your doors, okay, and the like. Given enough time, okay, if your heat source disappears, well, you're going to reach an equilibrium between the inside temperature and the outside temperature. Okay, your inside your house will be the same temperature as outside. The second law really says nothing. It says that if the inside heat source were to disappear, that this gradient between inside and outside is going to be eliminated, given enough time. Okay, what the second law doesn't tell us, it doesn't tell you anything about which path, okay, the system is going to take to accomplish this. But, okay, with this law of maximum entry production, it says that, okay, if you take a constraint and you change a constraint, like, for example, you open a door in your house, think about what happens. Okay, all of a sudden the system is going to seize the opportunity. It's going to shift most of that thermal energy flow, okay, through that open door. Okay, it automatically knows to do this. Why? Because it's going to be able to minimize the gradient as efficiently and as fast as possible. Okay, so here we're saying the system automatically selects the paths out of all available paths that will get the system to its final state, that will get rid of that temperature gradient as fast as possible. Okay, now, last thing we'll say here, just something to think about. If you extend this concept to the evolution of life in the biosphere. Okay, well, actually, this is a quote by a guy Swenson, a couple things here. It says, if the world selects those dynamics that minimize potentials at the fastest rate given the constraints, okay, and if ordered flow is more efficient at minimizing potentials than disordered flow, okay, then the world will select order whenever it gets the chance. Okay, if we think about our Earth, the Earth certainly has a whole lot of very big gradients, okay, that are big enough to foster the kind of growth we're talking about here, where we can get self-organization, for both living and non-living systems. Okay, here's a quote by a guy, Patterson. He says that the overwhelming majority of biochemists and molecular evolutionists who have looked into this matter realize that these, well, like the Bernard cell is a dissipative structure, they provide a very viable, perfectly natural mechanism for self-organization and for the genesis of life from non-living matter. It's quite likely, it's been hypothesized that the origin of life would have happened, okay, beneath the ocean, okay, where you have fairly good-sized gradients. Okay, you've got temperature and sulfur gradients there. This is very fascinating, I think, that when they fly weather satellites and airplanes up in the atmosphere and they actually measure temperatures, okay, what they find is that where you have some of the world's most complex ecosystems developing, some of the highest forms of order, they find that the temperature is actually lower there. Okay, and you might conclude that, well, why would that be so? Because those complex ecosystems, that high degree of organization becomes very, very effective and very efficient at reducing the temperature gradient between, the top of our atmosphere and the surface of the Earth. Okay, so I know we've got to sort of see everybody sort of coming in here, so I think I'm going to stop right here. Okay.
Thank you.
Thank you. Yeah.
I know there's one room if anyone wants to come into my 234 lab, 233 lab, then we can continue talking.
Okay, yeah, if anybody has questions, I've got some time before I got to pick up my kids. So,
okay.
yeah, okay.
All right. Thank you.
Mm-hmm.